here we excuse me, illustrate a trapezoidal approximation graph between point 8 and 1.2 with an increment of 0.2 for the function y equals x cubed plus 4. We put the values of the function next to the line segments that indicate the values, and I'll actually color code these for you. Okay, this value here goes with the purple line. The value 5 here goes with this purple line. The value 5.73 goes with this one. And we obtain these values just by plugging 0.8, 1, and 1.2 into this definition of the function. Okay, then, given those values, it's fairly easy to calculate the slopes. Okay, the slope is, well, between this point and this point, what's the rise and what's the run? The run is obviously 0.2 since these lines are vertical, and you have a distance of 0.2 between these 2 points. And the rise is what? Well, the height, this line has length 5, this line 4.512. If you subtract those, I think you get 0.488, sorry. And you divide 0.488 by 0.2, you end up with 2.44, and that does work out. Okay, and then you do similarly over here, so you get the two slopes. Okay, so we could kind of associate those numbers with the slopes, and we put a rectangle around any number that indicates the slope of the line that it's next to. That's our convention. Okay, then we trying to find a good color here. Okay, we can calculate the area of each trapezoid. Okay, the area of each trapezoid we think of in terms of finding the altitude at the midpoint of the trapezoid, which will be the average of the altitudes here and here. We call these altitudes, even though trapezoid only has one altitude, and it's officially the distance between the two bases measured perpendicular to the bases, using a different notation or different vocabulary for the trapezoids you get when you split up a graph. Okay, so we call these altitudes because they look like they go up, look like they have some height. Anyhow, if we average these two numbers, we get the midpoint height, and then if we multiply that by the width of the trapezoid, we get the area. And that works because for a graph trapezoid at least, we know that we have a right angle here. And if we take the height at the midpoint and construct the rectangle that has the same width but that height, well, that rectangle eliminates this triangle, but it adds this triangle, and this triangle is congruent to this triangle if this is the midpoint of this side. Okay, so just one way to reconstruct a trapezoid into a rectangle. And that's the way we want to think about it, because we have an interpretation of what this altitude, we often have an interpretation of what this altitude might mean in a given application. We'll get to that later. Let's just get the trapezoids. So we average, anyhow, these two numbers, and we multiply by 0.2, and we get something that's approximately 0.95. There are more significant figures out there, as you can tell from the number of significant figures here. But I rounded off because we didn't have a lot of room. Okay, and then we did the same with this trapezoid. We got the 1.06, and we put those numbers inside the trapezoid with circles around them. Okay, now there are a couple of other numbers, and these are accumulated areas. This is actually part of a trapezoidal graph that started back at 0 for this function. If we start at 0, 0, 0.2, 0.4, 0.6, then 0.8, we will have gotten 4 trapezoids up to this point, and each would have had an area. And if we add all those areas plus this 0.95 that we get here, we get this, and we call that the accumulated area through this trapezoid. And then if we add this area 1.06 to this, we get 5.31, which is an accumulated area here. And these accumulated areas have a very important interpretation, as we'll see when we begin applying this whole idea to some real-world type problems.